Hey everybody, welcome back to Quantitative Reasoning. Today we're in section 2.3 and we're going to be looking at Venn diagrams and set operations. So here are the objectives for today, and it looks like a long list, but each of these concepts is actually pretty short. We will talk about what the universal set is, we'll learn how to draw a Venn diagram, and we'll talk about the complement of a set, the intersection of two sets, the union of two sets. We'll use Venn diagrams to solve a few problems. We'll talk about the meaning of the words and or as they relate to set operations, and then we'll also learn how to determine the cardinality of the union of two sets. So let's go ahead and get started. So first of all, a Venn diagram is just a way to visually represent relationships between sets, because y'all know a picture is always worth 1,000 words. Venn diagrams are named after British logician John Venn, so in case you're wondering, the word Venn is somebody's actual name. So what do we mean by the universal set? Well, the universal set is a general set that contains all the elements under discussion, and it's always represented on the diagram by a rectangle. Subsets within the universal set are depicted by circles or ovals. So let's look at a couple of examples together. Example 1a says use the Venn diagram to determine each of the following sets. And so here is our first Venn diagram. Now in part A, they're going to ask us to determine the elements of the universal set. And so let's look at this diagram together. We said earlier that the universal set is always represented by a rectangle, and it contains all the elements that are of interest. This U is not an element in the set, but it is the label that tells us that this rectangle represents the universal set. And this A is also not an element, but it is just the label for set A, which is represented by this circle. These things here are all elements in the set. So everything that is an element inside the rectangle is an element in the universal set. So let's open a set of curly braces and just list all of these elements. So we've got the square, the triangle, the dollar sign, the M, and the 5. And of course, as we're listing elements, we separate each of them with commas. And then don't forget to close your set with a pair of curly braces. And now in part B, they asked us to list all the elements of set A. So again, we'll put equals and open a set of curly braces, but the only elements in set A are the square and the triangle. And then part C says list the set of elements in U that are not in A. So the set of tells us that we need to open a pair of curly braces, and now the elements that are in U but not in A would be the dollar sign, the M, and the 5. Here in example 1b, we're going to do exactly the same thing, but with a different universal set. So I hope you will pause the video for just a minute, try example 1b on your own, and then we'll go through it together. Okay, now let's go through example 1b together. So the elements in the universal set will be 1, 5, 6, 7, and 9. Don't forget to use the proper notation, so make sure that you list all of these elements separated by commas and that you put them inside a pair of curly braces. Now remember from earlier that the order of the elements doesn't matter. So I have them listed here in order from smallest to largest, but that is not important at all. If you listed them in a completely different order, your answer would still be correct as long as you have all the elements there. The elements in set A will be 1, 5, and 6. And the set of elements in U that are not in A would be the set that includes the 7 and the 9. Okay, now let's look at some different Venn diagrams and see what different types of set relationships look like on the Venn diagram. So one relationship we want to talk about is disjoint sets. In other words, two sets that have no common elements. So we would always have the universal set labeled with a U, and then we would have one circle that represents set A, and then another circle that represents set B, and the two would not overlap at all because they do not have any common elements. And then you'll remember from section 2.2 talking about proper subsets. So remember that in order for set A to be a proper subset of set B, all the elements in set A will also be elements of set B. So in other words, set A is fully contained inside of set B, but also the two sets are not equal if set A is a proper subset of set B. So on our Venn diagram, that would look like this. Of course, we have our universal set. Inside the universal set, we have set B. And then inside of set B, we have set A. So it's clear that set A and set B are not equal to each other because you see that there are going to be elements in set B that are not included in set A, but all of the elements in set A are included in set B. So that's a proper subset. And we could also have equal sets represented on a Venn diagram. So if set A equals set B, then A is a subset of B, and B is a subset of A. In other words, they share exactly all of the same elements. So what that would look like is we would have the universal set here, and then we would have one subset inside of our universal set, and since set A and set B are exactly the same set, the label would say that set A equals set B. So all the elements in here would be elements of both set A and set B. And then we could talk about sets that have some common elements, but then others that are not common. So if set A and set B have at least one element in common, then the circles representing the sets must overlap. So here again we have our universal set, and then we have a circle representing set A, and then we would have a circle representing set B. And you can see that the sets overlap, so there's room in this overlap for elements that exist in both set A and set B, but it's also possible for set A to have elements that are not part of B, and for set B to have elements that are not part of A. So here's example 2, and it says use the Venn diagram to determine each of the following over here. Okay, so notice that we have the universal set, we have set A represented here and set B represented here. Now everything in the circle for set A is part of set A, and everything in the circle for set B is part of set B. There is one element that is in both, so it's shown in the overlapping area, and then there are some elements that are not in either set A or set B, but they are part of the universal set. So in part A, they asked us to list all the elements of the universal set. So of course we open a set of curly braces, and you can see that the universal set contains everything that's in both set A and set B, and then these other elements out here. So we'll just list them going from left to right, but as we've said before, the order of the elements is not important. So the universal set contains A, B, C, D, E, F, and G. And then set B contains all the elements that are inside the circle for set B. So that's going to be the elements D and E. Set C asks us to list the set of elements that are in A but not in B. Okay, so the set of tells us that we need to list these in curly braces, and we want the elements that are in A but not in B. Okay, so look at set A. The element D is in set A, but it is also in set B, so we don't want to list that one. So we only want to list the A, the B, and the C. Then for part D, it says list the set of elements in U that are not in B. Okay, so look at what is in B. Inside set B, we have the elements D and E, so we want to list everything else. So the set of elements in U that are not in B would be curly braces A, B, C, F, and G. And then for part E, it says the set of elements in both A and B. Now there's only one element that is in both A and B, so this set would contain only the element D. Now you may have the hang of this by now, so if you would like to pause the video and try these next 4 on your own, I think that is a great idea. And when you've had a chance to do that, then we'll go through the answers together. Okay, so here we go. In part F, it wants us to list the elements of set A. So the elements of set A would be everything that's in the circle for set A. So that would be the set containing A, B, C, and D. In part G, it says list the set of elements in B, but not in A. So set B only contains 2 elements. One of them is also in set A. So in part G, the set of elements in B, but not A, would be the set containing E. In part H, it says the set of elements in U that are not in A. So look at what is in set A. We want to list everything else besides these elements. So part H would be the set containing E, F, and G. And in part I, the set of elements in U that are not in A or B. So if we want the set that contains only the elements in U that are not in either A or B, that would be these 2 elements right here. So that would be the set containing F and G. Now let's talk about the complement of a set. So the complement of set A, symbolized by A with an apostrophe, which we read this A prime. This represents the set of all elements in the universal set that are not in A. In set builder notation, it looks like this. A prime, or the complement of A, is the set of all elements X such that X is an element of the universal set and X is not an element of A. So basically everything else. Set A contains some elements. The complement of A contains everything else from the universal set that was not in set A. Here it is in the form of a Venn diagram. So the shaded region here represents the complement of set A, or A prime. A prime includes all the elements that are outside of the circle for set A, but still inside the rectangle of the universal set. And let's look at example 3 together. Part A says, let the universal set be the set containing 1, 2, 3, 4, 5, 6, 7, 8, 9. And let set A equal the set containing 1, 3, 4, and 7. Find A prime, or in other words, find the complement of A. So we're going to draw ourselves a Venn diagram just to make this easy to visualize. Let's start with a rectangle that represents the universal set. And then we know that inside the universal set we have set A. So I'm going to go ahead and put the elements 1, 3, 4, and 7 inside the circle for set A. Now all the other elements need to go in this space that's outside set A. So the 1 is already included in set A. We need the 2, the 5, the 6, and then we need the 8 and the 9. Okay, so now you can see that every element from the universal set is represented here. The ones that are outside of set A are A prime. So A prime is the set containing 2, 5, 6, 8, and 9. Here's part B. It says let the universal set be the set containing A, B, C, D, E, and let set A be the set containing A and D. Find A prime. Now we don't necessarily have to draw the Venn diagram first. You probably can just look at this and tell what the elements of set A prime ought to be. So let's go ahead and write A prime equals the set containing, and now let's see what ought to go in this set. We know that the element A is already included in set A, but the element B is not, so B is going to be part of A prime. C is also going to be part of A prime, and then the element D is included in set A, so it's not included in A prime, and then the element E is included in A prime. So again, if the universal set is the set containing A, B, C, D, E, and set A contains elements A and D, then set A prime contains everything else from the universal set. So that would be the B, the C, and the E. And if you wanted to draw it on a Venn diagram, it would look like this. So here's our universal set. The set A would contain elements A and D. Outside of that, we would have the other three elements, so the B, the C, and the E. Now let's talk about the intersection of two sets. So if A and B are sets, we can form a new set consisting of all the elements that are in both A and B. This set is called the intersection of two sets. And the symbol for the intersection of two sets looks kind of like an upside down U or a lowercase n, or maybe a horseshoe or something. It's not a letter, so I don't want you to think that this is a lowercase n, but it's just an arch, okay? And that's all it is. So that symbol right there represents intersection. And here is a formal definition for the intersection of two sets. So the intersection of sets A and B, written A intersect B, see there's that symbol. So this is read A intersect B, is the set of elements common to both set A and set B. In set builder notation, it looks like this. A intersect B is the set of all elements X such that X is an element of A and X is an element of B. And in example 4, let's practice with that. So it says find each of the following intersections. So here we have the set containing 7, 8, 9, 10, and 11. Intersect the set containing 6, 8, 10, and 12. And so the intersection will be a set. It is the set of all elements that are found in both of these sets. And so we'll say that the intersection of these two sets is the set containing the 8, because the 8 is found in both sets, and the 10, because the 10 is found in both sets, but that's all. Okay, in part B, we have the set containing 1, 3, 5, 7, 9, intersected with the set containing 2, 4, 6, 8. And there are no elements that are in both of these sets, so the intersection of these two sets is empty. So we could write it with the empty braces like this, or with the empty set symbol like that. And then in part C, we have the set containing 1, 3, 5, 7, and 9 intersected with the empty set. And you know that the empty set does not contain any elements. Therefore, these two sets have no elements in common, and therefore the intersection is the empty set. So you could write it again with the curly braces or with the empty set symbol. Here are a couple more. If you would like to pause the video and find these intersections on your own, you're welcome to do that. And now I'll go through these with you. So in part D, we have the set containing 1, 3, 5, 7, and 9 intersect the set containing 6, 7, 10, and 11. So the intersection would be the set containing the 7, and that's the only element that they share. In part E, we have the set containing 1, 2, and 3 intersected with the set containing 4, 5, 6, and 7. And again, these two sets do not share any elements, so the intersection would be the empty set, which you can write this way or with the empty set symbol. Now let's talk about the union of two sets. So another set that we can form from sets A and B consists of elements that are in either A or B or in both sets. And this new set is called the union of two sets. And this also has a symbol. So the union symbol looks like this. It almost looks like a letter U, but notice it does not have a tail on it. So it's the upside down of the intersect symbol that we just saw a minute ago. So let's get a formal definition for the union of two sets. The union of sets A and B, written A union B, is the set of elements that are members of set A or set B or both. And in set builder notation, it looks like this. A union B is the set of all elements X such that X is an element of A or X is an element of B. And in example 5, we'll practice finding the union of a few different sets. So in part A, we have the set containing 7, 8, 9, 10, and 11, union the set containing 6, 8, 10, 12. So one easy way to find the union is to list all the elements from the first set, so I'll go ahead and do that. And then list any elements in the second set that you don't already have from the first set. So we don't have the 6 yet, and we do already have the 8 and the 10, but we don't have the 12, so we'll put that in there. And that is the union of the two sets. Okay, part B says the set containing 1, 3, 5, 7, 9, union the set containing 2, 4, 6, 8. So let's go ahead and list all of the elements in the first set, and then we'll add the elements from the second set that we don't already have, and that just happens to be all of them. So we'll put the 2, 4, 6, and 8 in there, and there is the union of the two sets. The union is the set containing 1, 3, 5, 7, 9, 2, 4, 6, 8. And of course we know order is not important, so you could put these numbers in order if you want to. Probably when you're working in MyLab, if they show you a correct answer, the elements will be in numerical order, but remember that it's kind of like putting things in a Walmart bag. It doesn't matter what order your stuff gets put in the bag as long as it's all in there. Okay, and then part C, we have the set containing 1, 3, 5, 7, 9, union the empty set. So remember, the union is the combination of all the elements from both sets. So the union here is going to include the elements 1, 3, 5, 7, 9, and then whatever additional elements the second set contributes. But the second set here is the empty set, so it doesn't contribute any new elements, and so we just close the set. Now here is part D, and so I hope that you'll pause the video, try these last couple on your own. And now we'll go through them together. So in part D, we have the set containing 1, 3, 5, 7, 10, union the set containing 6, 7, 10, and 11. So the union is going to be the set containing the 1, 3, 5, 7, and 10, and then also the 6 and the 11. For part E, we have the set containing 1, 2, and 3, union the set containing 4, 5, 6, 7. So we'll go ahead and put down the 1, 2, and the 3, and then none of the elements from the second set have been included yet, so we'll go ahead and put down all of those. And the union of these two sets is the set containing 1, 2, 3, 4, 5, 6, 7. Now here is just a summary of how the empty set behaves anytime we have the empty set intersected with another set or union with another set. So we saw this in the previous examples, but any set A intersected with the empty set is going to give us the empty set as a result. And that's because the empty set has no elements, therefore it will never have elements in common with the other set. So any set intersected with the empty set is going to give you the empty set. But any set A union empty set is going to give you set A as a result, because again the empty set has no elements. Therefore, when we put the elements from set A together with the elements from the empty set, the result is just the elements from set A. Okay, now we're going to do some examples involving set operations. So some problems involve more than one set operation, and the set notation specifies the order in which we perform these operations. Always begin by performing any operations inside parentheses. So it's very similar to the order of operations that you're familiar with from previous math classes. So we'll always start inside the parentheses. Now let's take a look at example 6. So it says, given these three sets, find each of the following sets. And the set U that they gave us is the set containing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Set A is the set containing 2, 4, 6, and 8. And set B is the set containing 2, 4, 5, 9, and 10. And so the first set they want us to find is the complement of A union B. So remember that whenever we have parentheses, we want to find the set that's specified inside the parentheses before we try to do anything outside. So let's start by finding A union B, and then we can think about what its complement would be. So we know that in order to find the union of two sets, we put down all of the elements from the first set, so we'll include all the elements from set A, along with any elements from the second set that we don't already have. So if we look at set B, we already have the 2 included, we already have the 4, we do not yet have a 5, so we'll put that down. We don't have a 9, and we don't have the 10. And so now we have the union of sets A and B. Now the complement of this is going to be everything from the universal set that's not included here. So the complement of A union B is going to be the set containing, we'll just go through the universal set and include any elements that are not included in A union B. So we will need the element 1. We don't want to include the 2 because that's in the union of A and B. We do want to include the 3, but not the 4, not the 5 because the 5 is listed here. The 6 is included in the union, so it's not in the complement. We need to include the 7 in the complement, but not the 8 or the 9 or the 10. And so the complement of A union B is the set containing 1, 3, and 7. Now let's look at part B, which says A prime intersect B prime, or the complement of A intersected with the complement of B. So we don't have any parentheses here, but I think it's clear that before we can determine what the intersection is, we will have to find the complement of A and the complement of B. So let's start with A. So we'll find A prime. A prime is going to be the set containing every element of U that is not included in set A. So it will include the element 1, it will include the 3, and the 5, and the 7, and also the 9 and the 10. And then B prime, or the complement of B, is going to be everything from the universal set that's not part of set B. So that's going to be the 1, the 3, not the 5, but the 6, the 7, and the 8, and that's it. Okay, now the intersection of these two sets is whatever they have in common. So A prime intersect B prime is going to include the element 1 because they both have a 1. It's going to include the 3, and it's going to include the 7 because they both have a 7. So how interesting that although the two sets they asked us to find look completely different in set notation, when we actually list the elements of those sets, they turn out to be equal. So they turn out to be the same set. That's just interesting, isn't it? And now let's look at example 7 together. Now in this example, we are still doing set operations just like we did in example 6, but the difference here is that they've given us a Venn diagram to work with instead of listing the elements of the given sets for us. So actually this is better because a picture's worth 1,000 words, like they always say. And so I think you'll find that it's easier to see what elements belong in each of these sets by looking at the diagram. But before we get started, I just want to point out to you that this particular Venn diagram has the regions numbered. And so these Roman numerals that you see here, the 1, 2, 3, and 4, they are not actually elements of the set. In fact, let's just go ahead and blot those out because we won't need them. Okay, now in part A, they've asked us to find A union B. And we know that when we find the union of two sets, we want to include all the elements from the first set and all the elements from the second set, but there's no need to list any elements twice. Well, when we look at the Venn diagram, this circle contains all the elements of set A, and this circle contains all the elements of set B. So the elements in the set A union B would just be all the elements that are in these two circles. So it's going to be the set that contains 2, 3, 5, 7, 11, and 13. And now in part B, they've asked us to find the complement of A union B. So that's going to be all the elements that are not inside A union B. Well, you can see right here in the diagram, all the elements in A union B are in the shaded circles. And so the complement of that is the elements that are not inside the circles. So the complement of A union B is just going to be the set that contains 17 and 19. And now in part C, they've asked us to find A intersect B. Well, the intersection is the elements that the two sets have in common. And you can clearly see in the diagram right here where the two sets overlap only contains one element, and that is the element 5. So A intersect B is going to be the set that contains 5. And now let's look at part D. So here they've asked us to find the complement of A intersect B. Well, we talked about just a minute ago how A intersect B is just the set that contains 5. So the complement of that is going to be all the other elements besides 5. So that's going to be the set that contains 2, 3, 7, 11, 13, and 17 and 19. And now in part E, we're looking for the complement of A intersected with set B. So let's look at the diagram. The complement of set A would be everything that's not inside the circle for set A. So the complement of set A would be these 3 elements and these 2 elements. And then set B, of course, is this circle right here. So that would be the 5, 7, 11, and 13. Now the intersection of the complement of A and B is going to be what those two have in common. So if the complement of A is 7, 11, 13, 17, and 19, and set B is what's in this circle right here, then what they have in common is just the 7, 11, and 13. So A prime intersect B is going to be the set that contains 7, 11, and 13. And now in part F, we are asked to find the union of A and the complement of B. Okay, well remember that whenever we find the union of two sets, we start by listing all the elements from the first set, and then we include any additional elements from the second set that aren't already listed. So when we think about set A, we know that that includes all the elements inside the circle for set A. So we know that A union B prime is going to contain the elements 2, 3, and 5. Now, we need to also include any additional elements that are outside of set B. So here's set B, and the complement of B is any elements that are not inside this circle. So the only elements in B prime that are not included in our union here would be the 17 and the 19. So we'll add those. And so now we have that A union B prime is the set that contains 2, 3, and 5 because they belong to set A, and 17 and 19 because they belong to the complement of B. Okay, now the whole purpose of using Venn diagrams and talking about set theory is to help us have a way to analyze and think about situations that we come across in everyday English. So whenever we have a complicated situation and we kind of need to break it down into its components, that's what Venn diagrams and set operations are for. And so those things are just tools that give us a precise way of organizing, classifying, and describing all kinds of different things that we encounter in everyday life. So whenever you have a situation where the word or is used, or always refers to the union of two sets. And the word and always refers to the intersection of two sets. So again, or is for unions, and is for intersections. So just for an example, let's take this pie chart right here. This pie chart is supposed to represent the language spoken at home by the set of all U.S. Hispanics. So it says that 43% of U.S. Hispanics speak only Spanish at home, 32% of U.S. Hispanics speak only English at home, 23% of U.S. Hispanics speak both English and Spanish at home, and then 2% speak something else entirely, not English or Spanish at home. So here's how we could turn this into a Venn diagram. We could label the sets with U, S, and E. So U would be like our universal set, and that would be the set of all U.S. Hispanics because that's who's under consideration here. And then S could be the set of U.S. Hispanics who speak Spanish at home. E could be the set of U.S. Hispanics who speak English at home. And so we'll draw our universal set, and that represents the set of all U.S. Hispanics. Then we'll have a circle for set S that will represent the U.S. Hispanics who speak Spanish at home. And we'll have a circle for set E, and that represents the set of U.S. Hispanics who speak English at home. And you can see I've drawn it where the two sets overlap because we have this category of U.S. Hispanics who speak both English and Spanish at home. So our 23% is going to go in here. So our percent of U.S. Hispanics who speak only Spanish at home would be 43%. And then our percent of U.S. Hispanics who speak only English at home would be our 32%. The percent who speak both English and Spanish at home would be 23%. And then the 2% who speak something else would be outside of the sets S and E. So you can see that the set of U.S. Hispanics who speak both Spanish and English at home are represented by the intersection of the two sets. Okay, now let's use our Venn diagram to write the set notation for a few different sets that they've described here. So the first one is the 43% who speak Spanish at home and not English. Well, all we have to do is remember that the word "and" represents an intersection of two sets. So what two sets are being intersected here? Those who speak Spanish at home are represented by the set S. So S and, that's an intersection, not English. So those who do speak English at home are represented by the set E. So that means that those who do not speak English at home, well, that's everybody who's outside of set E. So that's the complement of E. So S intersect E prime is the set notation for the 43% who speak Spanish at home and not English. Now let's look over here at our Venn diagram and see if we can determine where S intersect E prime is. We know it ought to be the 43%, but let's make sure it makes sense. So the set S is representing the 43% who speak Spanish only at home and the 23% who speak both Spanish and English. So the set S includes both of these numbers. And then the set not E includes everything that's outside of set E. So that would be the 43% that we have here and the 2% that we have here. And we know that the intersection of the two sets is whatever they have in common. So you can see that that is the 43%. That's the only percent that the set S and the complement of E have in common. Okay, now let's look at the 32% who speak English at home and not Spanish. Okay, so again, the "and" translates to an intersection of two sets. So those who speak English at home are represented by the set E, and is the intersection. Not Spanish is going to be the complement of S, so S prime. And if we look at our diagram, those who speak English at home are the 23% and the 32%. Those who do not speak Spanish at home are everybody who is outside of the set S. So that's going to be the 32% here and the 2% here. So again, the only percent that is in both sets is the 32%, and so this is the correct set notation for this description. Okay, now what about the 23% who speak Spanish and English at home? Okay, well, that's even a little easier than the two we just did. The set for Spanish and English is going to be S intersect E. And we know that the 23% is just the overlap between the two sets, so that works out great. And then what about the 98% who speak Spanish or English at home? Well, so far every time we've had an and, so that's always been the intersection, but the word or is represented by a union of two sets. So that's going to be set S union set E. And so that would be the 98%, and so if you add 43 and 23 and 32, you do get 98%. It's everybody except these 2% right here. Now let's talk for just a minute about the cardinal number of the union of two finite sets. So the question here is, can the number of elements in A or B, in other words, the cardinality of A union B, can we find that by adding the number of elements in A to the number of elements in B? Well, let's look at this Venn diagram and let's think about it. So the cardinality of set A would be the number of elements in this circle here. So all of the elements in region 1 plus all of the elements in region 2. That would tell us how many elements are in set A. And then the cardinality of set B would be the total number of elements in this circle, so that would be all of the elements in region 2 plus all of the elements in region 3. So if we add the number of elements from region 1 and region 2 for set A to the number of elements from region 2 and region 3 from set B, well, you can see we've counted region 2 twice. So that's the problem. Adding the cardinality of A to the cardinality of B will cause us to count the elements in region 2 twice if there's any overlap. So in order to find the number of elements in the union of set A and set B, what we have to do is add the number of elements in A and the number of elements in B, and then subtract what's in the overlapping area because that's been counted twice. But how will we know what that number is? Well, that number is represented by the intersection of set A and set B. So here's the formula to find the cardinal number of the union of two finite sets. So the number of elements in A union B is equal to the number of elements in A plus the number of elements in B minus the number of elements in the intersection of A and B. So right here what we're doing is we're subtracting the overlap because it's been counted twice. So let's look at a real-life example in example 8. So it says, some of the results of the campus blood drive survey indicated that 490 students were willing to donate blood, 340 students were willing to help serve a free breakfast to blood donors, and 120 students were willing to do both. How many students were willing to donate blood or serve breakfast? So your first thought might be, well, why don't we just add the 490 students who were willing to donate blood and the 340 students who were willing to help serve breakfast, and the total of those will be the total of students who were willing to do one or the other. Well, the problem is these 120 students who were willing to do both, because this 490 is not the students who were willing to only donate blood. 120 of these 490 were willing to do both. See, the 120 are counted in here, but they're also counted in here. So that's where our formula comes in. Let's let set A represent the set of students who are willing to donate blood, and let's let set B represent the set of students willing to serve breakfast. And so the number of students who were willing to either donate blood or serve breakfast is going to equal the number of students in set A plus the number of students in set B minus the number of students in the intersection of A and B. So from the problem, we know that the number of students willing to donate blood was 490, so that's the number of students in set A. And we know that the number of students willing to serve breakfast was 340. And then we know that the number of students willing to do both was 120. So we just need to subtract that because those 120 students have already been included 2 times. So we just subtract them 1 time, so they're only counted once. And then 490 plus 340 minus 120 is 710. So there were 710 students who were willing to donate blood or serve breakfast. And let's look at example 9. So this says a bookstore kept track of their last 500 sales. They found that in the last 500 sales, 350 customers bought fiction books and 275 bought nonfiction books. How many customers bought both fiction and nonfiction books? Well, the fact that they are asking us to find the number of customers who bought both fiction and nonfiction books tells me that we're looking for the intersection of 2 sets. So let's go ahead and define our 2 sets. So we can say that the set A is the number of fiction sales and the set B is the number of nonfiction sales. Now remember that they're only looking at their last 500 sales, but you can see that of those last 500, there were 350 sales involving fiction books and 275 sales involving nonfiction books. Well, that's more than 500 sales. So that tells us that some customers bought both. And the problem is that the customers who bought both are going to be counted in this 350 number, but they are also included in this 275 number. So let's go ahead and look at our formula that we've been using and see if we can figure out the number of sales that are in the intersection of the 2 sets. So we know that the number of elements in A union B is equal to the number of elements in A plus the number of elements in B minus the number of elements in the intersection of A and B. So for this example, the number of elements in A union B is going to be our 500 sales because that's the total. All of these sales have to add up to 500. And then we know that the number of sales in set A was the 350, and we know the number of sales in set B is the 275, and then in order to get to 500 we have to subtract the number of sales that are both, and of course that number is what we're looking for. So what we want to do here is isolate the number of sales in A intersect B. So what we need to do is take the 350 and the 275 and move them over to the left side of the equal mark. So we'll have our 500, and then when we move, we say we move things to the other side of the equal mark, but what we really mean is we subtract it from both sides. So if I subtract 350 from both sides of the equal mark, it's going to disappear from the right side, but it's going to show up on the left side as minus 350. And the same thing for the 275. If I subtract 275 from both sides, it's going to disappear from here, but it's going to show up over here on the left as minus 275. And then I've got my equal mark, and then I've got minus the number of elements in A intersect B. So if we work out this number on the left side, 500 minus 350 minus 275, that adds up to negative 125. And then the right side is equal to negative of the number of elements in A intersect B. Now if negative 125 is equal to the negative of the number we're looking for, well that just means that positive 125 is the positive of the number we're looking for. So the number of elements in A intersect B is 125. So check it out. If you take your 350 fiction sales plus your 275 nonfiction sales, that's a total of 625. Now, if 125 of those were customers who bought both fiction and nonfiction, so you subtract out the 125, 625 minus 125 gives you a total of 500 sales, so that's correct. Okay, that's it for section 2.3. And I just want to encourage you, you may have seen some things in this section that are unfamiliar to you, maybe seem a little bit difficult at first. Remember that when something is new to you, it seems more difficult than it really is. So you may have to go back and listen again. Ask your instructor all the questions that you want to. They will be glad to help you. And just keep working on this, and I'll see you again in section 2.4. Bye.